In this video, we're going to cover the inner solar system debris. First, we're going to start off with asteroids, then we'll talk about meteors, meteoroids, meteorites, and then we'll end with comets. Asteroids are small chunks of rock and debris that drift between the orbits of Mars and Jupiter. They are often called minor planets, and in fact, one of our dwarf planets resides in the asteroid belt. They separate the terrestrial planets from the Jovian planets. Here are some of their orbital properties. Their orbits are fairly elliptical, which gives them a high eccentricity. Most reside in the asteroid belt, which is located between 2.1 and 3.3 astronomical units from the Sun. It is possible that the asteroids are primal rocks that never formed into a planet. It could be that there was never enough mass to form a planet. Also, we have Jupiter's gravitational pull, which has an influence on the formation of a planet at this location in the solar system. And that actually is where we get into what we call the Kirkwood gaps. This influence is actually seen in the belt itself. There are actually several locations where the asteroids do not reside in large quantities. These gaps are called the Kirkwood gaps, and they are the points at which there's a resonance between Jupiter and that location. The Kirkwood gaps are caused by a resonance, as mentioned before. As you can see, a gap indicated in purple appears at resonances with the orbital motion of Jupiter. Actually, in this picture, it looks blue, not purple. In the original diagram, it's purple. Okay, so here at 7, we have a 7:2 ratio for resonance. Notice how we have a decrease. Same thing at 3:1, 8:3, 5:2, 7:3, 9:4, and 2:1. Notice you also see a gap at 7:4, 5:3, and 8:3 as well. Or I'm sorry, 8:5. Okay, so basically what's happening is Jupiter is going around the Sun. It has a gravitational pull on these asteroids. As it works its way around, though, it continues to have a change in that gravitational pull. All of those gravitational pulls based on the eccentricity of the orbit of Jupiter causes specific locations in the asteroid belt to have sort of like a gravity multiplier. And that's what we mean by when we talk about resonances. Those gravitational pulls are adding together and causing a resonance at those locations, which then forms a gap in the asteroid belt. The two largest asteroids in the asteroid belt are called Pallas and Vesta. Sirius used to be the largest asteroid before it was reclassified as a dwarf planet. Sirius has a diameter of about 940 kilometers, which gives it a spherical shape. This is equivalent, just give you an eyeball figure on that, it's equivalent to about 584 miles. Pallas and Vesta are not spherical in shape. They don't have enough mass to give them that spherical shape. So here we find that these two, being the largest asteroids, are going to stay in the asteroid belt as asteroids. Most asteroids are irregular in shape. This can be seen from the top photograph taken of Ida from the Galilean spacecraft on August 28, 2003. In this photo, it shows Ida's rotation over a period of time. Asteroids with moons are called binary asteroids. If you look closely at Ida, you can see its moon Dactyl. Some asteroids in the asteroid belt actually cross the orbit of Earth and also Mars. The Earth-crossing asteroids are called the Apollo asteroids when their orbital axis exceeds 1 astronomical unit. Remember, 1 astronomical unit, or 1 AU, is equal to the mean distance between the Sun and the Earth. When the orbital axes are less than 1 astronomical unit, the asteroids are called Aten asteroids. Amor asteroids cross the orbit of Mars only. So those are your 3 types of Earth and Mars crossing asteroids. Here you can see the asteroid belt in blue. The Apollo and Aten asteroids are in pink. Keep in mind, though, that this has a width that changes because your Apollo asteroids have a greater than 1 astronomical unit radius, whereas the Aten asteroids are less than 1 astronomical unit. So keep in mind that this pink band is not that thin. It actually is pretty spread out. The Amor asteroid you can see in green. Now, on Jupiter, if you look at Jupiter, you'll see that there's clumps of orange on either side of its orbit. Those are called the Trojan asteroids. And they make about a 60-degree angle between Jupiter and Jupiter's orbit with the sun. So, the Trojan asteroids lie on what we call the Lagrange points. These are points in orbital resonance with Jupiter. They were calculated by the mathematician Joseph Lagrange in 1772. He calculated that there were 5 resonance points. The asteroids have been located at all of these points. However, the most stable resonances occur at your L4 and your L5 points. And actually, what's interesting about L4 and L5 is that if we were planning to have a manned mission to Mars, we would probably look at putting equipment at L4 and L5 in the orbit of Mars so that we could easily get materials from space to the surface. Asteroids will move into and out of the other Lagrange points, L1, L2, and L3. And that makes them appear stable, but they're not as stable as your L4 and L5. Okay, now there is a 60-degree angle between the sun and the L4 point and the sun and the L5 point. Okay, so let me show you this here. Right here is your 60-degree angle. It's on both sides. This is your L4. This one's your L5. Here on this side of the orbit, it's a point right here, is your L3. This is your L1 right here, and this is your L2 right here. Okay, so L4 sits right here on the orbit of Jupiter, and L5 sits right here on the orbit of Jupiter. Okay, so let's talk about asteroids in general. There are 3 main types of asteroids, the C-type, the S-type, and the M-type. The C-type asteroids are also known as carbonaceous asteroids. They appear dark in color and contain a large percentage of carbon. The C-type asteroids increase in number as you extend outward in the asteroid belt. They make up about 75% of all asteroids. Scientists believe that the C-type asteroids have not experienced significant heating or chemical evolution since their formation about 5 billion years ago. This would explain why they exist in the outer regions of the asteroid belt, where it tends to be cooler. The S-type asteroids are highly reflective and appear to be rocky and reddish in color. They may also contain silicates, which is sand. They are only located in the inner part of the asteroid belt or closest to the sun. They make up about 15% of all asteroids. The final type of asteroid is called the M-type. These asteroids are predominantly nickel and iron rich and may be the iron cores of fragmented asteroids. These asteroids are believed to be formed in the inner regions of the asteroid belt. So now we're going to talk about meteors, meteoroids, and meteorites. A meteor is a streak in the sky caused by friction between the Earth's atmosphere and an asteroid, a comet, or a meteoroid. A meteoroid is a chunk of interplanetary debris before it hits the Earth. A meteorite survives the atmosphere and actually lands and hits the ocean or the ground. So, how can you remember the difference between the meteoroid, the meteor, and the meteorite? What I would do is this. This is how I remember it. Think of a meteoroid as being in the voids of space. A meteorite holds tight to the Earth, and anything in between the void of space and the tightness of the Earth is going to be our atmosphere, where we have meteor. So if you remove the voids of space, you have a meteor. If you remove the tightness of the Earth, you have a meteor. So that's how I remember the three of them. So as I said in the previous slide, meteoroids are believed to be pieces of asteroids or other solar system debris that move through space. It can actually be pieces of planets as well as comet debris, and also pieces of asteroid or pieces of moons. Okay, once they hit the ground though, they become a meteorite. Most meteorites are formed from asteroids through collisions. So if you take a look at the picture on the right-hand side, you can see an asteroid. It's a large planetesimal. It's been internally heated for a long period of time. That means that the inside is going to be able to become heavier, and the outer layers are going to be less dense. So the more dense materials are going to move towards the center. The outer layers are going to be less dense. As we see collisions taking place between this asteroid and other debris, pieces of it are going to break off. Those pieces that break off are your meteoroids. The meteoroids then collide with the Earth and become meteorites. Okay, notice though the material that gets knocked off the most. It's the outer shell, which is your silicates. Okay, so we're going to produce more meteorites that are silicates or stony in nature versus the iron, which we have at the core of the asteroid. Most of the meteorites that are found on the Earth are iron-based meteorites. These meteorites appear different to the eye and they're easily spotted. In fact, only 6% of all of the meteorites that hit the Earth are iron-based meteorites, but 66% of those are actually found. Now, the more common meteorites, which are the rocky silicates, 92% of all of the hits that we get from meteorites are the stony type. But look at how much we find. We only find 26%. So you may be asking, well, wait a minute, Dr. H, Dr. Hing, how do you even know this? How do we know if we're finding more iron? Why isn't there more iron? Well, it turns out that there was a scientific team that was sent to Antarctica, and what they did is they roped off areas in the ice and counted off the different types of meteorites that they found. And so what they did was they counted up all of the meteorites they found, and they clicked one clicker for the stony and one clicker for the iron. And so that's what ends up giving us these numbers. So they had 92% that they found were actually stony or rocky meteorites, and only 6% were the iron type. Okay, so that's how they figured out that we have 92% stony and only 6% iron. Now you may be thinking, well, that doesn't add to 100%, and it doesn't, because there's always something else. Remember, I said that it could be debris from a comet, it could also be from a moon or another planet, and that makes up the difference in the percentages. Okay, so here in this picture, you can see the difference. If you look at the meteorite on the left, that's an iron meteorite. It's very heavy for its size, and it has dark, irregular surface to it that's also shiny or metallic. The stony meteorites, though, if you look at that, they tend to have a fusion crust caused when it's entering the Earth's atmosphere. But if you were to just look at that in the woods, you might say, oh, that's an interesting rock. And then you might just leave it there. But if I found that iron meteorite in the woods, I'd be taking that home. I'd be like, look at this. This is a meteorite. Okay, so you can see the difference in how they look and why we find more of the iron meteorites than the stony meteorites. Okay, so now let's talk about impact craters. There are still some craters that are visible, and several others that have been actually found through space observations and also through gravity mapping. The most well-known and best preserved is the Barringer crater. This crater is nearly a mile wide and is located in the Arizona desert. So here you can see it's about 200 meters deep, 1.2 kilometers wide. The Yucatan crater has recently been discovered in Central America. The ancient Indians used the sinkholes produced at the rim of the crater for religious sacrifices and burials. These sinkholes were actually mapped out by the National Geographic team, and you can see them by this the white dots in this photograph. That's how they were actually able to discover this crater, okay, because they started mapping out these sinkholes for what the research work they were doing, and they saw that it actually formed like a circle, like it looked like the rim of a crater. Okay, this crater is large, and it's actually believed to be about 100 to 300 kilometers wide. It is also believed to be the impact that actually killed the dinosaurs or caused the dinosaurs to go extinct. There's actually evidence in this crater of iridium. Iridium can cause the winters to last for many years. They actually found traces of iridium at the end of the Cretaceous period, and that's why they believed, and it was actually Dr. Luis Alvarez that made that discovery. I can't believe I remember him, but I do. So anyway, they found this layer of iridium, and it's believed that this crater is the source of that iridium that they found at this Cretaceous layer all throughout the world. Okay, there's also the Chesapeake Bay crater. I'm going to let you, I'll put the link for this on the website for you in Blackboard. It's about 100 kilometers wide, and we believe that this crater actually existed on dry land. The ice from the Ice Age melted, and that's what flooded the area. The crater is now under the water in the bay, and you can actually see the actual melting of the rock material from the impact. It's actually quite impressive. Okay, Tunguska is another impact crater. This actually occurred in 1908. The impact could be heard 1,000 kilometers away, and it actually lit up the sky to the point where in Great Britain they could see it. It is in Siberia, and we believe, based on the evidence, that it was probably a comet or probably an Apollo asteroid. Meteors are small pieces of rock or dust that burn up in the atmosphere. Meteor showers produce a beautiful show of these shooting stars. A meteor shower is produced by the Earth's orbit crossing the orbit of a comet. The dust that's left behind by the comet burns up in the atmosphere. The shower may also be produced by a comet that has broken up into many pieces and has spread along its orbit. Meteor showers can occur once or several years in a row as the Earth continues to move through its orbit. These meteor showers are predictable. So let's take a look at the stages. In stage 1, the comet breaks up into larger pieces. Right here you can see stage 1. In stage 2, the pieces continue to break up into smaller pieces. And right here is stage 2. Notice how they're breaking up into smaller pieces. And these pieces will continue to break up. In stage 3, there's no 3 here, but there's stage 3. The pieces continue to break up, but they also start to spread along the orbital path, which you can see here. They're starting to spread out along this path right here. In stage 4, which we have right here, the Earth passes through that debris. So here's the Earth on its orbit, moving through the orbit of the debris. And that's what produces the meteor shower. So meteor showers can also be caused by dust that's left behind by the comet. Meteor showers are usually named by where you can see them. So for instance, the Leonids can be seen in the middle of November in the constellation Leo. And that's where we see the radiant. Notice in this diagram here, the table, the radiant, they give you the coordinates, the right ascension and declination in space on your celestial sphere. That tells you where you can look, and that's where the meteors appear to be coming from. Now, this does not mean that by looking at the radiant, you're going to see every meteor. That's not the case. But when they streak across the sky, if you trace back in space, all of the places that they appear to come from, it's going to appear to come from the radiant. Okay, so in Leo is in, I will tell you this, the Leonids occur in April, but it's like 4 o'clock in the morning, at 5 o'clock in the morning. And at that point, the sun's starting to rise. And so it's quite difficult to see the Leonids. They're actually better, you're able to see them better if you're in like Japan. Another set that I'd like to bring up is the ones that occur in August, the Perseids. August 10th to the 14th, these have been brilliant in the past couple of years. Actually, a couple of years ago, I was actually on a beach in Chincoteague, laying on the beach looking at the Perseids, and they were gorgeous. I mean, they were just streaking across the sky. So if you ever get a chance to go out and take a look at one of these meteor showers, the Taurids are coming up, the Orionids are coming up 18th to the 23rd. So that's at the end of this week. If it's not cloudy, go ahead and see if you can see anything. Now keep in mind, if you look at the hourly rate on this chart, the hourly rate changes per year based on what part of the orbit we're going through. Okay, so the Perseids, when this chart was made in 2005, we're only showing about 40 per hour. Couple of years ago, it was up to 140, 180 per hour. So it will change, and you'll need to look at an updated chart to see. If it's only 15 or 8 per hour, you're going to be very lucky to see anything, because it takes just not even a nanosecond, it seems, for that meteor to shoot across the sky, and then it's gone. So by the time a friend can say to you, oh, there it is, it's already gone. So I would take a look at this chart, look at these dates, because these showers will always occur on these dates. But take a look at the internet and check out and see which ones are going to be closer, or have a larger hourly rate, and also appear in the dark. I mean, you don't want to have the meteor shower peak in the middle of the afternoon. You won't see anything. I'll go ahead and take a look at the links, and I'll post a link for you. Okay, so now we're going to talk about comets. In 1950, Dr. Fred Whipple came up with the current theory on the composition of comets. He coined them dirty snowballs because he believed they were a mixture of ice, dust, and rocky particles. The central region is the core or the nucleus of the comet. Around the nucleus is the coma. The comet is gas and dust that surround the nucleus. The hydrogen envelope wraps around the nucleus and the coma. There are two tails that form when the comet approaches the sun. As the comet comes closer to the sun, the ice begins to melt and thus forms the tail. When the comet moves away from the sun, the comet becomes cooler and does not release that gas and dust, so it disappears. Now, there are two types of tails. There's the gas tail, which is a type 1 tail, and the type 2 tail is the dust tail. The tails will always point away from the sun. Okay, here's the other thing. The gas tail will always line up directly with the sun, whereas the dust tail will actually curve towards where the comet used to be. So as this comet nucleus moves in its orbit around the sun, the debris is going to burn off and be released, but it's going to take a little bit longer for it to move. So the dust tail is going to be curved and the gas tail is going to be straight. So in order to tell the difference in looking at a picture, one, you can look at color. Okay, so the dust tail is going to be produced by reflected light. So it's going to appear white in color. Whereas the gas tail is actually produced by the atoms or the molecules of those gases actually becoming excited by the radiation of the sun hitting them. So there's going to be a releasing of electromagnetic radiation based on that the gas getting excited. Okay, so the dust tail is reflected light. The dust tail is reflected light. The gas tail is emitted light. So sometimes the gas tail will look blue in color versus the dust tail having a white or a clear color. Okay, so that's the best way to tell. The gas tail will also be straight, whereas the dust tail will sometimes be curved. Okay, like I said before, the dust tail always points away from the sun. The Kuiper belt is where short period comets reside. The Oort cloud is the outer regions that contain most of the comets. And we're going to talk about these two in, actually, I think we already talked about them in the solar system. Remember that the Oort cloud is theoretical. We don't actually know, and we haven't actually observed the Oort cloud. Okay, so short-term period comets are going to be in the Kuiper belt. The outer regions are going to be where most of the comets seem to reside, which is your Oort cloud. Okay, so let's talk about some popular comets. Halley's Comet is the most popular, but it's not popular because it's pretty to look at. Okay, it's actually not a very spectacular comet to view. But what is important is that Edmund Halley realized that this comet in 1682 was actually orbiting the sun, and it was going to actually reappear in 76 years. Okay, he didn't live to actually see the reappearance of the comet, but the comet was named after him in honor of him. His predictions actually changed our view of comets. They were now orbiting objects and not just objects that pass by us once. So for instance, Shoemaker-Levy is another famous comet. This is one that actually collided with Jupiter. Okay, once we were able to figure out from Halley these calculations of orbits, we were able to calculate the orbital periods of all of the comets that have passed by us. Okay, so as we talked about in the Jupiter lectures, Shoemaker-Levy crashed into the surface of Jupiter. It was traveling, or the pieces were traveling about 36 to 37 miles per second. It was a huge, huge explosion, 750 times the world's nuclear arsenal. Remember, the bomb that was dropped on Hiroshima was only 0.15 megatons of TNT. The impact crater was about 12,000 kilometers wide. It stayed there for quite a while. There were dark spots on the surface of the planet, what we call the surface. Remember, it's gas, so there's no real surface. But it was darkened in those areas for quite a while. Okay, here's another popular comet. This is Hale-Bopp. It's actually quite beautiful. It appeared in 1997. Again, here you can see that the dust tail appears blue in color, and the gas tail is blue. The dust tail appears to be white. And notice how the dust tail appears to fan out and bend slightly, whereas the gas tail appears to go straight. So if you were to follow that gas tail back towards the core, the nucleus of your comet, and then keep going, that's where the sun would be located. Now, I'm not sure if any of you remember this, but Hale-Bopp was actually known by unfortunately, a cult in California that actually committed suicide because they were planning on being transported to a spaceship that was behind this comet. So that's a very sad history about this comet, but it is beautiful to look at.